Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe Newton's theory of gravity. So, you know, um, everybody's probably heard the old story about the apple hitting Newton in the head, and I kind of doubt that that it unfolded that way. But I think there is probably some truth that I think he was sitting in an apple field once and observed an apple falling or something. And the first major deduction that he came up with was, he observed an apple, which he observed accelerating down, meaning that, when an apple was falling, you could pretty well see that the apple's speeding up. So its velocity vector getting larger and larger and larger. And in Newton's theory, in Newton's laws of motion, Newton's second law is net force equals ma. So within his theory, he had to come up with a force to create that, and that's a force he called the gravitational force. So in a free body diagram, if I were to pick one of these apples here and draw a free body, I've already done that. The free body looks something like this. We have one force down, and by Newton's second law, that force is equal to mass times acceleration. Now remember that acceleration is rate that velocity changes, and we can write it out formula-wise a couple different ways. I wrote it here once. Acceleration is delta v over delta t. Again, these are both vector quantities. This is what I would call the algebraic equation for acceleration. This gives the average acceleration over a time interval. Or we can write it in the language of calculus, which I've done here. Acceleration is equal to dv dt, or the time rate of change of velocity. Again, either one is accurately gives what acceleration is. This gives the average acceleration over time interval. This gives the instantaneous acceleration. Now, it's also said that, one of the big things that Newton connected was this, that whatever force is accelerating the apple was also accelerating the moon. He came to the conclusion that the moon was orbiting around the Earth. So what we're looking at over here is a picture of the Earth here, and kind of a schematic. We got the moon, and the moon's moving in a roughly circular orbit around the Earth. And by Newton's second law, F equals ma, if you believe something's accelerating, there's got to be a force to accelerate the object. It requires force to accelerate a body. And because the moon is moving in a circular path, if we think about a velocity vector like in this position and a velocity vector later, you can see that these velocity vectors have changed in direction. Hopefully you've seen my video about centripetal acceleration, but the moon here is accelerating, and that acceleration is due to the changes in direction of these velocity vectors. That's a centripetal acceleration. So because the moon's accelerating, there has to be a force required to do that. And it's said that Newton's first big revelation here was that the force accelerating the apple and the force accelerating the moon were of the same type, were the same thing, and that's what he called the gravitational force. Right? Now it takes things to cause a force. Force is always an interaction between two bodies. But the million-dollar question is looking at this apple right here. The million-dollar question is, what is it that's actually creating the force on the apple? Like if I were to put a surface around it, what is it within this surface here that's creating this force, right? And here's where the theory part starts coming into play. Newton said, well, I'm not quite sure what's creating that force on the apple, but I know something's doing it. I'm going to give it a name. And that's what he called the gravitational field. Now, like in English, when you start using a new word, you have to go define it somewhere. So the first steps here in Newton's theory of gravity is to define the gravitational field. He defined it in terms of force and mass. He said to himself, I could take an object and I could measure the force on it, the force of gravity on it, or what we would call its weight, and I can also, through an experiment maybe accelerating it horizontally, measure its mass. So the gravitational field is defined as the ratio force over mass. Right? So the gravitational field has units of Newton per kilogram. Now if you work it out, by Newton's second law, a Newton is equal to ma, mass times acceleration. So Newton has units of kilogram meter per second squared. So dimensionally, a Newton per kilogram is the same thing, or is equivalent to meter per second squared. If we do any experiment at the surface of the Earth where we measure the gravitational force on an object, divide by its mass, we get a value of about 9.8 Newton per kilogram. And you'll notice that, the object, if we drop it, it accelerates down at about 9.8 meter per second squared. Gravity normally is taught as an acceleration, but really that's not, I don't believe that's actually accurate here. If we look at the free body, like I have right here, and in the absence of any other forces, when we apply Newton's second law to this apple, it looks like this. Sum of all forces equals ma. My standard rule of thumb, identify the acceleration direction, call that positive. We have one force, what we call the gravitational force. And because of Newton's theory of gravity, it's not too hard to show that, put the m on the left, that the gravitational force is equal to mg. So we've got mg, this would come from Newton's theory of gravity, equals ma. The equals ma is coming from Newton's second law. And in this case, the masses divide out, and you notice that g, the gravitational field strength, 9.8 Newton per kilogram, is equal to the acceleration of this object, 9.8 meter per second squared. Now, it almost seems like the same thing, but they're not. Remember, this thing right here is a field strength, has units of Newton per kilogram. The acceleration has units of meter per second squared. The only reason they're numerically equal is that there's no other forces. As soon as we include any other force, like maybe some air drag, so I'm going to draw another free body of this apple. Give me just a moment. All right, so if I think about, a different free body of the apple, a free body after the apple has sped up pretty fast, then air drag would become a relevant force here. So, we would have the gravitational force, which I usually label mg. But if the apple's moving pretty fast, like maybe we dropped it off a tall building or something, eventually air drag becomes a factor. I'm going to put a little f sub a for air drag here. Now the apple's still accelerating down. When we write our Newton's second law equation, this is going to be sum of all forces equals ma, down positive. The Newton's second law equation for this free body is now mg minus f sub a here, being whatever the air drag force is, equals ma. When we solve for the acceleration, now we're going to get g minus f sub a over m. Now you'll notice that the acceleration is no longer equal to g. The acceleration is going to be something less than g by whatever this factor is. So again, the acceleration and the gravitational field strength are different things. And gravity hasn't changed. The gravitational force and the gravitational field strength in this free body is the same as in this free body. It's just that the acceleration is now different because there's another force acting there. So, in this equation, really this term right here is from Newton's theory of gravity. Now, you can measure the gravitational field strength anywhere on the surface of the Earth, and you're going to get about 9.8 Newton per kilogram, give or take. That third decimal varies depending on where you're at, but I don't think the second one does. However, over in this case here, the gravitational field strength a long way from the Earth is not equal to 9.8 Newton per kilogram. The further you get away from the Earth, the weaker and the weaker and the weaker the field is. So I'm going to take a moment here, pause this, and create a new picture. All right, folks, I'm back here. So what we're going to start talking about now is how the gravitational field varies around a pretty large mass. So this picture right here, just ignore this for now. I'll bring this in when this is relevant. This picture here is, maybe the Earth or some other large planet. It has a mass m. Now, the reason I wrote m here, usually when you're talking about gravitational fields and you're talking about gravity in a very general sense, usually one of the objects you're dealing with is of planetary mass. So usually one of them is very, very large. So again, this m here is a capital M representing the mass of what is typically some very large object, asteroid size or higher. It doesn't have to be, but usually it is. If you want to talk about relevant gravitational fields, one of the masses needs to be planetary size. or the mass creating it, I should say, needs to be pretty much planetary size. So in Newton's theory of gravity, he would say, whatever this object is, it creates this thing around it called the gravitational field. And if I were to pick a spot like right here, right, the gravitational field would point inward. That's because of how it's defined. Right? It's defined as force per unit mass, meaning you would, in theory, put a mass here, measure this force, measure the force on it, divide by the mass. But the force is an attractive force, the gravitational force. And because of that, the gravitational field always points towards the mass creating it. Technically, we're talking about towards the center here. Now, if we go further away, the field strength should get weaker. If I go further away, the field strength should get weaker yet. All right. So putting a couple things together at once. First, let's talk cause and effect. What's causing the gravitational field? Well, in Newton's theory of gravity, the mass of this planet is what he believes is causing the gravitational field. And in the theory, he assumes a direct proportionality relationship, that the gravitational field strength is proportional to the mass creating it. Now, direct proportion. If G is proportional to M, that means that G is equal to some constant times the mass. The constant is called the gravitational, universal gravitational constant. It's usually written with a capital letter G. The numerical value of that constant, I'll write it over here, is 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. Right, the units will be clear why that is here when I get this finished up. So this is kind of like the first part of Newton's theory of gravity, that the gravitational field is created by the mass, therefore the field is directly proportional to the mass. Now, the distance factor. There is a distance from the center of this planet to whatever point we're interested in. I'm going to call that R. The field strength is a function of R. And by observation here, at least, we can see that, the further out we go, meaning the larger R is, the weaker gravity tends to be. Right? That's a property of what's called an inverse type of function. Well, it turns out because of the type of symmetry we have, this problem has spherical symmetry. If I come over here and I measure a gravitational field strength, it should be the same as here if I'm equal distance out. And if I come up here, same thing. If I come down here, same thing. I'm not going to draw that one. As long as I'm the same distance out, the gravitational field should be roughly the same. So there's a spherical type of symmetry here, meaning that the mass of this planet is creating an effect out in space here that's spherically symmetrical, or another way we can think of that is it's creating the effect on the surface of a sphere surrounding it. And spheres have a radius, spheres have an area of 4 pi r squared. And the 4 pi not important, but the r squared is. And what that means is if you double the radius of a sphere, you multiply the area by a factor of 4, or we would say that the area is directly proportional to r squared. Right? So what that means over here, if I pick a point in space, you got to imagine a sphere that is that goes through this point. In fact, I think I can just create one here for us to talk about. I'm just going to put this in green. So imagine it like this. This mass is creating an effect on the surface of a sphere out here. That effect is what we call the gravitational field. If I make the sphere larger, in fact, imagine that I double its radius, the same mass is creating an effect, the gravitational field, on the second sphere, but the second sphere has 4 times as much area roughly because it has double the radius. So we would expect the gravitational field to be cut by a factor of 4. All right, so getting to the end of this, that means that in our mathematical formulation of this, the G is inversely proportional to not just R, but R squared. So for the reasons that I just discussed. And I think I'll make another video here about why it's r squared on the bottom. But for now, let me kind of put this together as simple as I can. So we would say in Newton's theory of gravity, this mass creates something in space around it called a gravitational field. Because the field is created by mass, then the field strength is directly proportional to mass. And that's basically the top half of this equation. The gravitational field G equals a constant times m. Right? But the gravitational field gets weaker with distance. As we get further and further and further and further, the gravitational field needs to get smaller and smaller and smaller, meaning that G is inversely proportional to r. But it isn't just r, it's r squared for the reasons I talked about earlier about the sphere. Right? This really is Newton's theory of gravity right here, that the gravitational field strength is proportional to m, falls off with r squared. Combining it with this, notice if I take this mass and put it over here, we end up with the following equation for force. Big G, big M, little m over r squared. So I would call this step 2 of the theory here. So here's how the gravitational field is calculated. And because the force, if you look right here, if I put the mass over on the left, this equation would read F equals mg, right? And g is equal to this quantity. Therefore, the gravitational force is proportional to the two masses, falls off with r squared. All right, so this is what I would call step 2 of Newton's theory of gravity. Now, I'm going to get through the energy part of this as well. The gravitational force is a force where we can define a potential energy. And, when you're dealing with constant gravitational fields, we would normally say that the potential energy is mgh. Right? This is perfectly fine if the gravitational force, which is the mg, is constant. But if you start looking at kind of a planetary scale, it's easy to see that it's not constant here. Here we have a force that falls off with r squared. So what I'm going to do here is I'm also going to go through and talk about an expression for the gravitational potential energy. That's where my little TIE fighter here is going to come in. All right, whenever I'm talking about spatial type of things, I usually draw like a little TIE fighter. They usually look something like this, but I actually went out and found myself a little TIE fighter to put in this video here. All right. So as far as the potential energy, imagine this TIE fighter starting out like maybe right here. And then, imagine it now moving off into space until it's gone, right? So I'm going to draw the original point right here, but we're going to be considering it moving over to the right until it's infinitely far away. The gravitational force, actually, give me just a moment, I'm going to put it right there. We're going to move it off into this direction. The gravitational force acting on that TIE fighter, due to the interaction of the planet, would be towards the center of the planet. So I'm going to go ahead and put a force vector, and so that we can distinguish it here, I'm going to put that in blue. All right. Boom. So there is a gravitational force equal to this expression, this G big M little m over r squared. Now, as the TIE fighter moves off, and it doesn't matter through what mechanism, maybe through its own power or something, as it leaves. All right, so imagine that TIE fighter moving in this direction. The gravitational force is falling off. I'm going to take a minute and just sketch a plot of the gravitational force against distance. So if we were to graph force against time, that force, or not against time, I'm sorry, against distance, I'll say against r here, that force looks something like this. It has some value when we're at this position, but as we get further and further and further away, it falls off. So that this function has a shape. It looks kind of something like this maybe, right? Now, work. In order to calculate the potential energy, we have to calculate the work done by gravity as this TIE fighter leaves. the work done is going to equal the area under this curve here. So I'm going to go ahead and write out an expression for the area under that curve. Now, if you've had some calculus, this will not be too bad, but if you haven't, that's okay. You can just follow along for a little minute, and I'll bring it back together here at the end. So the area under this curve is going to look like this. The integral from the first position, which I'm going to give a name here, R1, because that's going to be a starting value, to the second position. Now the TIE fighter's way out here. I'm just going to call that R2 for now. The force is defined by this function, big G, big M, little m over r squared. Right now I want work, so that's force times distance. We're going to call that a dr. This is all constant, so it can come out in front of the integral. The integral of 1 over r squared dr is minus 1 over r. Whoops, and that reminds me, I got to go back just a little bit here. Remember what I was calculating was the work done by gravity, and you'll notice that the gravitational force is left, but the TIE fighter is moving right. So because of that, I'm going to put a minus sign here because the work done by gravity is negative as this TIE fighter leaves. See, the force is basically down and left, but the TIE fighter is moving right. The force and the displacement are in opposite directions. So that minus sign would be here. And then again, the integral of 1 over r squared dr is minus 1 over r, evaluated at these limits, r1 to r2. Now, this product is positive, so we get g, big M, little m, let's see, over r2 minus big G, big M, little m over r1. Right? So now, this expression represents the work done by the gravitational field. And hopefully you've seen my video about potential energies and how they work. The change in potential energy for a system is equal to the opposite of the work done by the field. So the change in potential energy here of our system is actually going to equal this. Let's see, big G, big M, little m over R1 minus big G, big M, little m over R2. So now we're going to take a look at this. Notice that these change in potential energy terms, they have R's at the bottom. And with potential energy, you typically have to pick a datum. So I'm going to go ahead and do that. Taking note that these terms are 0 when the R's are infinite. So this is quite common in problems like this. We're going to imagine the datum for the TIE fighter being 0 infinitely far away. So we would say that the datum's at infinity, which means this term would be gone right here, because R2 is going to infinity, which means the change in potential energy is equal to this expression. Now, change in potential energy is PE final minus PE initial. And it's not too hard, looking at this expression to show that the potential energy term then, PE initial, is equal to minus big G, big M, little m over R1. And this is the potential energy terms for Newton's theory of gravity. So I'm going to kind of write this out in a more general form here. I'm going to take a minute, clean this video up, and kind of put this all together here, hopefully. Give me just a second. All right, I'm back here. Here's what we're looking at. I've cleaned my picture up. So right here, what we're looking at here is just some planet with a reasonably large mass. Over here, we have some sort of object here. I traded my TIE fighter for the Millennium Falcon. Newton's theory of gravity, in a nutshell, in 30 seconds or less, is large masses, or actually any mass, but typically we're talking about a large mass, create this thing around them in space called the gravitational field. The field always points inward. That field is proportional to the mass creating it, falls off with r squared. Right? What do we do with this? Well, what that means is that if I put an object here, or somewhere close to it, let me put it over here, then there's going to be a gravitational force on that object. Oops. And that force is equal to the mass of the object times G, And by time you take this, insert here, what we end up with is big G, big M, little m over r squared. Right now, I showed the force on the Millennium Falcon here. Keep in mind there's also a force on the planet because forces always appear in pairs. Newton's third law. Those pairs are always equal magnitude, opposite direction. In addition to that, we would say that the system also has a potential energy equal to minus big G, big M, little m over r. That's pretty well it in a nutshell. Oh, how the gravitational field is defined. Let's get that in there too. Gravitational field is defined as force per unit mass. So really, I would say these 1, 2, 3, 4 equations really are Newton's theory of gravity in a nutshell. And this really is the first one. That's the start of the theory. Gravitational field, this is how it's defined. Force per unit mass, Newton per kilogram. Second part of the theory is here. This is how Newton surmised that the field should vary functionally, or how it should be calculated. Proportional m falls off with r squared. Third part, putting these two things together, this is how a gravitational force should be calculated then in general. Big G, big M, little m over r squared. And then fourth part of the theory, so this is part 3. Fourth part of the theory, because of this force and area under the curve, the potential energy terms should look like this: minus big G, big M, little m over r. This video has already gotten pretty long, so I'm going to hold off my examples for later. Typically, in Newton's theory of gravity, one of the masses is pretty large of planetary scale, or perhaps both masses are. But the theory does apply really to any two masses. You have a gravitational field around you as well. It's just that it's a very, very, very small field here. Anyway, I think that's enough for now. Hope this video helps. Have a great day.